All right, welcome. Today, we are diving deep right into the heart of your computer, your phone, pretty much any smart device to answer a really big question. What is an operating system?
Think about it for a second. You tap an icon on your screen, and boom, this incredibly complex application just springs to life. It feels like magic, right? But it's not. It's the work of this powerful, mostly invisible piece of software. So what's really going on under the hood?
Okay, so to wrap our heads around this, let's start with a great analogy. Probably the best way to think about an operating system, or OS for short, is to imagine it as the conductor of a huge, complex orchestra. Now, a conductor doesn't actually play an instrument, right? They're not playing the violin or the cello. Instead, their job is to manage the entire orchestra, the timing, the volume, who plays when, all to create this beautiful, harmonious piece of music. Well, the OS does the exact same thing for your computer. It doesn't run your web browser or your game itself, but it manages all the computer's hardware, the processor, the memory, the storage, so that all your apps can run together without turning into a complete and utter chaotic mess. And this quote really gets to the heart of the OS's two fundamental jobs. First, it manages the messy, complicated hardware. And second, it presents a clean, simplified version of that hardware to our applications. So in a way, it's both a tough manager and a very clever translator. So how does it actually pull off these two huge jobs? Well, it all boils down to three core responsibilities that every single modern operating system has to handle. Let's break them down. Yep, these three functions, managing resources, providing abstractions, and enforcing protection, they are the pillars that make all of modern computing even possible. So let's take a look at how each one really works. First up, resource management. Just picture the OS as the ultimate traffic controller for your computer's limited resources. It's constantly juggling all these different programs that are screaming for CPU time, for a slice of memory, for access to the hard drive. The OS is the one that decides who gets to go, when they go, and for how long. It prevents total chaos and keeps everything running as efficiently as possible. Now this is one of the most powerful ideas in all of computing. See, a software developer doesn't need to know the specific brand of your hard drive or the super intricate details of how it stores bits on a magnetic platter. No way. Instead, the OS provides this beautiful, simple abstraction. It just says, hey, just use these three basic commands: open, read, and write. The OS takes care of all the messy, device-specific stuff behind the curtain. It basically creates what we call an extended machine that's just so much easier to program for. You ever wonder why a single crashing app usually doesn't take your entire computer down with it? This is why: protection. The operating system builds these strong virtual walls around every single program that's running. Each program is tricked into thinking it has the whole computer all to itself, completely isolated from everything else. This is absolutely crucial because it ensures one misbehaving app can't just scribble all over another app's memory, or, even worse, crash the OS itself. Okay, so we know what the OS does. But how does it maintain this incredible level of control and protection? Well, to understand that, we need to peek inside the OS structure itself. Modern operating systems divide the world into two very distinct zones. First, there's user space. You can think of this as the Wild West. It's where all your applications live. They have very limited privileges, and they absolutely cannot touch the hardware directly. And then there's kernel space. This is the protected inner sanctum, the very core of the operating system. Code running in the kernel has full, unrestricted access to everything. This separation is the secret to how the OS enforces protection. So, if an app in user space can't touch the hardware, how does it do anything useful like save a file? Well, it has to ask the kernel for help. And this formal request is called a system call. It is the only legitimate way for an application to cross that boundary into kernel space and ask for a privileged operation. Think of it like a citizen having to fill out a specific form to make a request from a government agency. There are strict procedures you have to follow. Now, when you launch an application, the OS creates something we call a process. And a process isn't just the program's code that's sitting on your hard drive. No, it's a living, breathing instance of that program. It includes the code, sure, but also all the memory it's using and its current state, like what exact instruction it's about to execute next. The OS manages all of these processes, and that's how it keeps track of everything that's running on your machine. And all this leads us right to multitasking. You can be listening to music, browsing the web, and have a chat video open, all seemingly at the exact same time. Well, this is actually a really clever illusion. On a single CPU core, only one thing can run at any given nanosecond. The OS creates the feeling of multitasking by switching the CPU between different processes hundreds, even thousands of times per second. It happens so ridiculously fast that to our brains, it feels like everything is running all at once. Of course, this incredible capability wasn't just built overnight. It's the result of decades of innovation. So let's take a super quick look at how we got from the earliest computers to the powerful devices we all have in our pockets today. Way back in the 1950s, computers ran one job at a time, in a batch. You'd literally hand a sack of punch cards to an operator and come back hours later for your printout. The 1960s, though, brought a revolution with time-sharing systems like Multics, which let multiple users interact with one giant computer at the same time. This was the direct ancestor of modern OS design. Then, the 1980s put that power on our desks with personal computers, and by the 2000s, operating systems were sophisticated enough to fit in our pockets and powerful enough to run the entire cloud. So let's bring all this home. Let's see how this invisible engine actually works in a simple, everyday task. Let's circle all the way back to our original question. What happens when you launch an app? Let's take a really simple example from a Unix-like system, like Linux or macOS. When you type a simple command like ls to list your files, a fascinating two-step dance begins. First, the terminal program, we call it the shell, makes a system call named fork. This tells the OS, hey, create an exact duplicate of me. And for a split second, there are two identical shell processes running. Then, immediately, that new child process makes another system call, exec. This one basically tells the OS, okay, now completely replace me with this new program, ls. The OS then loads the ls code into that child process's memory and starts it running. That classic two-step, fork and exec, is how most programs get started on these systems. So why does all this technical jargon matter to you? Because these core OS features are what create the smooth, stable experience you expect from your devices every single day. Multitasking, that's the illusion that lets you stream music while you type up a report. Protection, that's the safety net that stops a buggy game from taking your whole computer down with it. Abstraction, that's why you can plug in almost any brand of mouse or keyboard and it just works. And resource management, that's how your OS can give your video call priority so it stays smooth, even while a huge update is downloading in the background. When you really step back and look at it, the operating system is a master of illusion. It takes a physical machine with finite, complex, and messy hardware, and it creates this virtual world that feels simple, clean, and seems to have almost infinite resources. It is truly the unsung hero of modern computing. Which leaves us with one final thought. As our computers get even more powerful, what do you think is the next great illusion they're going to create for us?